Hello again. This is the second video in this four-part series about how to get started on Big Red 2 over at Indiana University. And again, I'm using my notes file on the right here, and I'm going to be running all my commands on the left. And the first video was about exploring the system, and the second one is actually going to go through a couple of examples of how to actually compile and run stuff. So we're going to go into this directory called MPI examples. Again, very simple code. I actually have the source code here. I actually have a C code and a Fortran code. This is I got this out of some book or something. It was a shifter. Basically, you set up a bunch of nodes, a bunch of ranks, let's say, and basically the ranks just get data from the left and pass it to the right, and just pass it around the ring and sum it up. So that's what this looks like. We're going to use the Cray compiler to start with, and again, if you do a module list, you'll get that list. I'm using a batch shell, so if I do this kind of fancy piping, I can just pull out the Cray environment. And I also wanted to show you there's also an environment variable called PEENV, and this is actually very useful if you want to make a very generic make file that would run for many different kinds of compilers. Some compilers might have different options that aren't available in other compilers. So you could do test on this environment variable to put in options that are specific to a particular compiler. So we have the Cray compiler loaded, and this is what's very interesting and important when you're running in the Cray programming environment on this system, is that you always use the functions or the commands cc for the C compiler, ftn for the Fortran compiler, and large cc for the C++ compiler. And I know if you go to GNU, it's going to have gcc, but you really don't want to use gcc on this machine. What you want to do is you want to swap from the programming environment Cray to the programming environment GNU, and then under the covers all the wrappers will get changed such that CC maps to GCC. And you also don't want to use MPI CC. That's all baked into these wrappers, and by default the Cray MPI library will be loaded for you. So you always use just these three compiling commands. So we're going to compile the C code. This is what a typical compile command would look like. This is what it would look like in Fortran. I'm just kind of proving that the source code does compile. And then we've got some source file, some source code. We've compiled it. We've made executables. I can prove that by doing an ls. There's my executable. This one's actually going to be the Fortran one because I did that one last. And now we have to make a batch script to run this thing. And I like to call it .moab if I'm on a Moab Torque system. If I'm on a PBS or an LSF system, I'll call them something else. Just a couple of basic, probably more than you need. This names the job. This gives the job some kind of a limit on the wall time. This says I want to grab two nodes, and I want each node to have 32 cores. So I'm basically grabbing two nodes worth of resources, 64 cores. This says combine standard out and standard error into one file, and then this says push the batch job's output to a file called testmpi.log. This says interpret this script as a batch file, and -v, I believe, exports your current environment. This line here says whenever you execute this command, change directories into that same directory where you executed the command, so that you're in the same spot so you can find all your files. And as we saw before, this is the app run command. Little n says launch this on 40 ranks, and I'm going to run this job. So now to launch that job, I'm just going to say Q sub this, and then I would do a QStat minus A to check on the status of that, and I'm going to pipe it through my filter because there's so many jobs on this machine. And you can see this Q here, which means my job is in the queue. And hopefully I won't have to sit here too long. There we go. We've switched from a Q to an R, which means that my job is running. And this job does really nothing at all, so it should exit pretty quickly. And there it is. So now we have a C, meaning that the job completed. And then if we want to look at the output from this job, very simple. It's going to give me 40. We ran this with 40 ranks. So I have 40 people saying that they're alive and 40 people saying, I'm starting up, initializing, and I have a certain value and I'm passing it around after so many shifts. Alrighty, so that was all done with the Cray compiler. And then this is kind of the example of how to, if I wanted to now do this with a different compiler. So you can see that I still have the Cray compiler loaded. And here's my swap command. So I'm now saying, let's use the PGI compiler. And I can look at my module list again. And now I see that the PGI compiler is loaded. Or I can look at my environment variable. Remember it said Cray before. Now it says PGI. And this is the really nice thing about this is that to recompile my code, all I do is I do the exact same command. And all the wrappers will point me to the new directories where all of the PGI libraries and the PGI compiler executables are at. And if I wanted to, I could submit that job again and see that this C here is from my previous job that had already completed, and that Q means that my new job is in the queue. And maybe we should wait for it. There it goes. It's running. And it's completed now. And just for completeness, there's the output again. So it ran. All right, so that's a very, very simple MPI code, and it's a very good one to just get started and learn how to do it. So now I have these hello examples, and this gets a little bit more into job placement. Give you some examples on kind of trickier launch commands. Scrolling up here a little bit. I'm going to swap back to the Cray compiler. And I'll prove that I got that. And there's Cray. All right, so here's the hello C. This one's a little more complicated. It's actually going to be pulling information about where the job is actually running. I'm going to compile it. Again, here's my batch script. So I'm going to run this job actually 3 times. I'm going to ask for resources. I'm going to ask for one node. Here's my node. I'm going to ask for, it's going to have 32 cores. I'm just giving it 30 seconds like before. These are fast jobs. And what I'm going to do, I'm going to run it once, and I'm going to run it with 32 threads. So this is with OpenMP, and it's one executable that's going to spawn 32 threads. And then I'm going to run it again, and I'm going to say, run it once with only 16 threads. And by the way, put those on that first run, put those threads on these cores. And then run that job again, run it with 16 threads again, but put those threads on the other 16 cores on the node. And then here's another example where I'm going to run it 8 times. Each time I'm going to run with 4 threads, and each time those 4 threads will be different cores within the machine. So yeah, I'm not sure where you'd use this in practice, but if you are really getting down into the nitty-gritties of what the machine is doing and really fine-grained placement, this is just to show you that you can control pretty much everything in your job. So there's my job. It's called hello, and it's in the run state. Oops, that was a mistake. There we go. It's still running. It takes a little longer because I'm actually running it so many times. And now it's done. And if I look at my output, it pretty much does what I said it would do. So here's my job, 32 one rank. It's an MPI job, but has only one rank. It has 32 threads, and you can notice that for every thread in the first job, the thread number matches the core number. Okay, then here's the second job. Here's the first date. So again, thread 14 ran on core 14, and then on the second time, thread 0 ran on thread 16 as opposed to instead of core 0, it ran on core 16 because I forced the job to run in the other set of cores. And then here it is again for the 8 jobs. All right, here's another example. And this is more of an MPI example than an OpenMP example. I'm going to compile it while I talk here. There's my batch job, and I want to get this submitted. And in this example, same thing, 2 nodes. I'm running on 2 nodes now. And this time, I'm going to ask for 16 cores per node. So I'm going to force it to go. This is a 32-way job, and I'm going to run it on 16 ranks per node. So this is going to force this job to run across 2 nodes. And if I check the output, there it's done. And there it is. And so now we have an MPI job, which has 32 ranks, an OpenMP job that has only 1 thread. And if you'll notice that the first 16 ranks got placed on 1 node, and the second 16 ranks got placed on another node. Alrighty, now on to something a little bit more complicated. And again, these are kind of advanced topics here, but you might find them useful. So I have many users that have asked me about how to run multiple jobs. So the machine schedules resources on a node basis. So if you have a single core job and you run it on this machine, you're going to run it on one of the cores of the node, and the other cores are going to be sitting idle. So if you have lots of small serial jobs, you can pack them together and run them on the same node at the same time. And it's actually really simple. Just what you have to do is, instead of launching the job with app run, you launch a script with app run, and then that script will then launch all the jobs that you need for that you want to run. I'm going to run this program I wrote clean, that just kind of cleans up the directories, gets rid of all the old output. Make is just a one-line, simple make the command. And then here's my batch script. So this is what I'm going to give to Moab, and I'm going to say I want 1 node, 32 cores per node. But instead, and here's my app run command, I'm doing some core affinity. I can actually make this 23-0. I mean, you can put any kind of core sequence in there if you want. But you'll notice that I'm running a job called test6x4.sh. So this is a batch script instead of an executable. And if I look at that, that looks like this. And so this script says, OpenMP, run my executable, and pipe it to a unique output file. And this ampersand in batch mode, in bash scripting, will put it in the background. So this will launch, and this job will launch 6 jobs all at the same time, all in the background, all on the node that you've submitted your app run command to. And then this wait here at the end says, just sit here at the end of this batch job or this script and wait for everybody to finish, and when they're finished, then return the results. So I'm going to go ahead and run this, And we're in the queue. So again, this is something that you would do if you had a lot of little jobs. There are other mechanisms to do, and there are other programs that can maybe automate this a little bit more, and we can research those later. But this is a good way to kind of hand roll, just getting a bunch of small jobs scheduled to the machine. And there's my job. I got the queue there, and it's running. Making some output. Oops. I want to do this command again. And I'm completed. Alright, so then this is kind of interesting here that the output from the log file from the batch job itself has no output in it because it's just all the output from the individual jobs got redirected to different files. So the log file for the whole job is very empty. And I can kind of prove that they all ran at the same time because if you look at the creation time, I'm doing this all just past midnight. You'll see that they all got created at the same time. And then if I look at all those files, here is that same Hello World program with the core affinity, so you can see that I'm running on different cores all at the same time. Alright, so that's the end of video 2, and this was on how to compile and run codes. And we'll start up in a few minutes with the next topic on cluster compatibility mode.